Welcome to the lecture on computer animation from the course series on computer graphics at KAUST. Today we will be talking about some high-level aspects of computer animation. So far, in computer graphics, we have described most of the aspects which are related to the structure, describing the geometry, describing how this geometry should be illuminated, etc. Now and then, we have mentioned a time, for example, when a curve is parametrized and we have a parameter which can be, through its increments, can simulate a drawing over time. Now, the computer animation at its heart is adding the temporal aspect to the 3D computer-generated geometry represented on the screen. And this adds totally another level of complexity because suddenly we have shapes which need to be animated, which need to change their shape over time, change various properties over time. And this has to be all somehow made in a continuous and natural way. Computer animation is also inspired by so-called traditional animation approaches. Back in earlier days, animation studios have created cartoon representations where each frame was representing one snapshot of time of an evolving structure, an evolving story, and these frames were stacked together, and when they were played back, then the appearance of or an apparent animated sequence have been generated. This is somehow very time-consuming and tedious, requires skills of an animator to be a good drawer on the top of making a good story. Often in animation studios, the so-called master animators would be creating the keyframes of an animation, and then the more junior animators would create the frames in between, which lead or to connect those keyframes. And this is, for example, one approach which has been adopted into computer animation. So within our now three-dimensional scene, very often we would place the scenery in a certain constellation for a given time frame, and then as the time advances at some other time, there will be a slightly different constellation of the elements in the scene, and in between we will be having the possibility to perform the other frames through automated process. And here, for example, we will be using the interpolation to give us the free frames in between. This is not the only form of computer animation. There are several other techniques. For example, procedural animation, where we define a certain procedure, how structures should be animated. That could be done in various ways. Procedural animation can be done by defining a certain process, which is then iteratively performed, and per each iteration, there is one step of this procedural animation generated. An example or subset of procedural animation could be physics-based animations, which are simply the procedures are the rules of physics, an implementation of Newtonian physics into a simulation could be a realization of a specific procedural animation, just realizing the effect of forces upon a given structure. An interesting aspect is another approach which is not done by in 3D environment, but it is following the strategy of by example type of generating animated sequence. So, for example, we might have in our 3D scene an 3D geometric mesh of, of an actor or of a figure in that story, but we would like to animate it with a real human animator, so kind of an analogy to a puppet and a puppet master. Here, however, we would be the human actor will perform the actual movements which are desired to be mapped on the object in the 3D generated scene through the motion capture. So this actor will be moving in the scene, and at each step of or sampled time step, we will be extracting some positional characteristics of his or her body. And these positional characteristics will be then transferred onto the geometry to animate the geometry. Several flavors of animation can be already seen here, and we will start giving you a brief overview on how such a computer animation can be realized. So let's start with the keyframing. You can see that a sequence of a typical movie would be a set of frames. However, you would like to define some frames which are somehow more important, which are sort of related to the storyboard which has been created before the animation sequence has been fully drawn. And these keyframes can be then interpolated with various interpolation schemes. So you can, for example, imagine that you put a car in over time in one position, and at another several time steps later, you put it into another position, and then you are interpolating the frames in between and moving the car effectively by that. And for this, I will just draw a single sphere. This will be let's say the time step 0, and if I will have the same sphere at the time step t1, what I can do is to perform a linear interpolation between these two positions. So I will have a vector of its position, and these two vectors could be component-wise linearly interpolated to change between the time steps, or let's call this time step 10, so that we have the in-between time steps 1, 2, 3, 4, 5. So let's call it time step 6. So that these time steps will be then interpolated. Of course, it doesn't necessarily need to mean that we will be interpolating with a linear interpolation. There could be different interpolation schemes. If we will be modeling a car, for example, it will be quite unusual that it will start with an instantaneous speed and then break from high speed potentially to 0. So there is often something called ease in and ease out, which might look like this in terms of amplitude of the velocity, if you can interpret this abstract curve which I draw here. So if this would be a graph, I draw it here. If this would be a graph, the velocity might go approximately like this, where this is the velocity and this is the time. So here we are coming to a certain description of how this keyframing can be authored. Not only that we are placing the positions of objects in the scene, and an interpolation should be done between these two positions through, let's say, linear or higher order interpolation, but we can actually author the process of this traversal, and it could be authored directly visually on such a velocity versus time curves or position versus time curves. Let's have a look at it in more detail. The keyframing should affect the position as we explained it on the previous slide, but not only the position, for example, orientation, rotation, but also other properties. For example, a color or size of objects, or even not only the geometry, but also the scene properties such as light, the illumination, and this illumination can also change over time of its position. Maybe think of a sun which is traversing the scene and or the dome around the scene, its strength, color, and orientation. These are all aspects which would be used in traditional movie making, and they are important in computer animation. Not only for making movies, but also, for example, in the game industry, this is a very important aspect as well. Increasingly more and more, such computer animation is relevant, or computer animation aspects are relevant in 3D visualization, where we are trying to automatize the computer animation process for discovering insights in scientific data. Of course, the camera will be also changed. So we can imagine that we are navigating through the scene either through a walkthrough or flyover or fly through. Various approaches are used in order to perform the change of position of a camera. Its projection parameters can be also changed. So we can change, for example, its focus, where we are having a different sort of a depth of field settings. A focal plane can be defined at one position, and then we can animate how this focal plane changes from one position to another. So pretty much everything in our 3D scene, not only the geometry, the object itself, but all the aspects in the scene can be animated and is animated in order to create an effective computer animation. Such change over time can happen in various ways. So I have already mentioned to you a linear interpolation between two positions. Imagine that we have a curve along which an object should move or a camera should move. We have discussed this already on the lecture on curves. So once we are moving this along such a curve, it is important that we have a certain control about this new movement. So it could be that if we are moving over time along a certain curve, then we have our points in time defined somehow equidistantly. We might define as an author some keyframe positions, as we can see here, with the black arrows, and the system can interpolate in between the positions so that they are more or less uniformly distributed over the timeline. But this doesn't need to be always the case. It just depends on our interpolation function. Sometimes another approach is desired. Like, for example, we can see here another interpolation scheme where the keyframes are placed exactly in the same way as on the example on the top. However, the interpolated frames are placed totally differently. One might think that this would be probably not a very nice animation sequence. Similar example is the third one, where we see that the interpolation is very close to the actual keyframes, and there will be practically no time spent on the intermediate positions along the curve. This will result in a probably quite some erratic movement rather than a smooth traversal of a scene or a smooth motion of an object. And this control over how an object should be moving can be not only specified directly in the 3D space, but also in the parameter space. Like, for example, here in the graph, we can see that there is a certain time evolving and there is certain function which is changing over time. This function can be, for example, a velocity, for example, or it could be just simply a position of an object in y dimension, let's say. And we can see that the author can, in such a space, define the positions, and then there is some interpolation scheme. We see here that this would be some higher order interpolation scheme in this case, so that these points are being interpolated. And not only that we can deal with the actual original function, but we can also look at the differentiation of such a function and observe how does the differentiation look like. For example, whether it is continuous or it is becoming discontinuous, or directly influencing the differentiation curve in order to then steer the shape of the first order or zeroth order curve shape. So there are various ways how we can author this, and we will be talking about that in a second, a little bit more in detail. Before that, however, let's talk about parametrization. We have been talking about parametrization on the previous lecture on curves, and we mentioned that parametrization can lead to the fact that a distance in the parameter space, parameter t, is not always resulting in the same distance along the curve. Sometimes, if we are drawing a curve, there could be a large distances and suddenly very small distances along the curve, which would mean that if we will be using just simple function over time and position as the curve is parameterized, the effect will be something like a roller coaster. So on the areas where there is a very short, very long distances, this will be time-wise perceived as passed by very quickly, while there are several time steps next to each other, there will be a slowdown of the speed. And this might be desired, but it should be desired or achieved in a controllable fashion. We can see here, for example, such an example of a not equally spaced parametrization. You remember how we called this parametrization, which should be then uniform along the curve? It was an arc length parametrization. And we have been discussing on the previous lecture what is an arc length, how to analytically express it, and how to compute the arc length for a given curve. And now we want to create a parametrization of the arc length so that we have a uniform time difference and space traversal difference, if you like, along the curve. How to do it? Well, we mentioned the analytical approach already before. However, this is not always possible, and because such an arc length computation might not have a closed form. For that, we can resort to an approximation, and as often in graphics, an approximation of the elegant mathematical solution is often sufficient. So a simple approximation of an arc length parametrization can be done through so-called forward differencing method. Here, instead of looking at the entire curve as a smooth curve, we will be approximating it as a set of linear segments. And of course, this would lead to a shorter curve than the original one, because the linear segments are then shortening effectively our curve, but there will be certain error associated, which we say we would tolerate. Maybe it will be an error which will be below the human perception, and it will be still apparently smooth process. Therefore, we can express our traversal of the curve as a set of linear segments along by a equally distant steps in the parameter space. Here we have our parameter space called U. And we see that there are different steps always. The delta U, if you like, will be 0.2. This leads to different lengths of our segments. We can see that the first segment is rather long, and then the second segment is higher because this is increasing curve, but it's comparably the difference will be shorter, and this corresponds to the drawing above. So we perform the calculation of the lengths of these linear segments and sum them up together in order to calculate the arc length at that position. And here is the formula to calculate that. So you can see that for a particular position U, we can take the previous position of the arc length, which we have already calculated, then calculate and then add to that the difference of the length, which is the length of the small segment. Here, this formula is showing us how can we calculate the intermediate steps of an arc length parameterization. We will come to that in a second. So once we have our elements, once we have created our forward differencing, we can store it in a table like this. So then we will have a lookup for U. We can always find the closest SU. And that we can use for an arbitrary U now to approximate the SU at that position. And we use this formula as is explained, plus we use this term here, which would be simply the linear interpolation factor, which will be telling us how far are we between the two segments. So for example, let's say SU will be 0.3. No, sorry. U will be 0.3, and we would like to know the position at 0.3. So how do we calculate it? Well, we need to find the SI, which will be the 0.2 U, so it will be 2.5. SI equals 2.5 in our case, and then the SI plus 1 will be 4. So SI plus 1 is 4, and then we are calculating what is this fraction here of U terms. So UI is 0.2, and yes, and we are calculating the U 0.3. So 0.3 minus 0.2 will be 0.1, and 0.4 minus 0.2 will be then 0.2. So 0.1 divided by 0.2 will be the scaling factor of the difference between these two arc length approximations. So our final formula will be 2.5 plus 1/2 and 4 minus 2.5. So we have here 1.5 will be the result, and the half of 1.5 will be 0.75, and 2.5 plus 0.75 will be something like 3.25. So for 0.3, the arc length will be 3.25. Simple calculation using this forward differencing table. However, we are often interested not to calculate the U from given U and SU, but the other way around. We would like to have a control. We would like to go through the SU in a monotonic linear way by equal increments, and we would like to calculate what is the corresponding u necessary for that. So in some sense, we can calculate it similarly to the calculation we have made for the SU, or we can use a more advanced numerical methods to find the U for a given S. And that we can use for reparametrization to have the arc length parametrization achieved. So for example, we have a parameter. Now we have a parameter S and U as we have defined, and then which is the parametrization along the curve. The U is the parameter for a curve parametrization. The T here is the time of the animation. And in our animation, we have a function of st, which is telling us how should our position change over time. So let's say this is just a one-dimensional change in positions, and you can see that over time the position is changing this way. We can even see that somehow here the position is increasing, and here it is decreasing, and here it is increasing again. So there will be some here and there movement from such an animation. However, these positions is on a curve. So we are going forward along a curve, then backward along a curve, and then forward, because we want to use this arc length position, which is defined this one, as a position along a given curve. But in order to be able to realize such a movement, we do not need to know the arc length, but we need to know the actual u value of such a curve, its parameter value of the original parametrization. Therefore, we need an SU parametrization. So this would be the arc length parametrization, which will, for a given point S, will give us the value of the U. And then we can actually put this value into this U value for a given time over time in the animation. We obtain a point on the arc length which we want to achieve. For that, we need to compute the given U, and that will be the parameter which will be then putting us into the position along the curve. So this is the way how an arc length parametrization can be achieved for computer animation. And we can see that the curve PU here is now, we are not directly parameterizing it by the parameter T, because that will result in an uncontrolled behavior, but we are instead, the parameter T is parameterizing our position along the arc length, and this parametrization along the arc length is then using this forward differencing function in order to compute the U, which we then use for the parameter for our curve positioning. Such a way, we achieve a highly controlled positioning along a curve. And keep in mind that the position along a curve is just one aspect which we might potentially want to control. The functions can be even made more difficult in a way that we are not defining the arc length distance versus time curve as it is, for example, defined here, but we might want to define a velocity curve. Often we are interested in order to profile certain velocity transitions. And such a profile will then need to be first mapped from velocity to an arc length distance, and then to the parameter u. So, or sometimes we are interested to define not the velocities, but actually accelerations. So from that, we would need to compute the velocity first, and from the velocity, we would need to compute the distance. As we know from physics, the simple description of a constant velocity would be that the distance is can be calculated as the velocity times over time. And the acceleration can be computed if the acceleration is in place, so there is not a constant speed, then we can slightly change the formula that the arc length is the some initial velocity over time plus the acceleration term, where we see that the time is powered by 2. And all these formulas between velocity and distance can be calculated from a differential expression of a of the relationship between these physical quantities. So, for example, and we can see it nicely on our graphical representation. I will just remove these scribbles here so that this will be more clean and easier to explain. If we have, for example, acceleration in place, then we are looking at acceleration as an acceleration curve. For example, it can be described like this. So we have an constant acceleration. So we are imagining we have a car and we are increasing the speed from given a constant acceleration to a certain point t1, and then we have a zero acceleration, which means that we are keeping the constant speed, and then we are performing some negative acceleration, so we are performing deceleration. And actually, the area under the curve is corresponding to what? Is corresponding to the integral of this acceleration function, and the integral of this acceleration function is actually the velocity. So this area here is defining us what will be the velocity at this position, at the what will be the velocity reached at the time t1. So if we will have some time in between, ta, let's say, the smaller area will be the velocity obtained until the time ta, for example. So here we are changing and increasing the velocity with such a plot, and with the integration we can calculate what will be the given speed, which will be the given velocity at a particular time. And if we want to ensure, for example, that a car starts with zero velocity, v0 equals 0, and the v end equals also 0, then we need to ensure that this area is the same as this area, because we need to, by the deceleration, decelerate to the speed of 0. So these two areas would need to be the same. The time doesn't need to be the same, the time duration, because the deceleration can be stronger, the amplitude can be higher for the deceleration than for the acceleration. It's important that the area is the same. And from that, we can calculate, based on our integration, we can calculate this velocity time curve, and by a next further integration, we can calculate the time distance curve. And this time distance curve is then used in order to find the parameter u through our arc length parametrization, and then put that into the parametric expression for of the curve so that we obtain the position along a curve. Positions are one part of transforming objects within computer animation. And the next very important type of transformation will be rotations. Imagine rotating a camera or a light source, for example, or rotating an object in our scene. How can we do that? Well, intuitively, we can think of that we are having two rotations or two states. One state is the starting rotation, and the next state is the target rotation into which we want to rotate the object or the camera to. And between these two, we would like to interpolate. Well, what are our representations for rotations? Well, we know that we can rotate with multiplying, for example, with a matrix which has a rotational component in it. That could be one way. In translation, for example, we can linearly interpolate if we want to interpolate along a line, we can linearly interpolate the XYZ coordinates independently from each other from one position to the next one. But can we do that? And we can do that also when we are having purely translational matrices in the form of a homogeneous coordinates, that we can do as well. But can we do that for rotations? And the answer is interpolating component-wise rotational aspect of the matrix will not work. We can see here why is this the case on a simple example. Let's have a look at one type of one rotational setting. So, for example, we have one matrix which we start rotation from like this. So this is clearly a rotational matrix. We can see that based on the components of the two vectors which are perpendicular to each other. And then we have another rotational matrix which also encodes rotation, just that the rotation is slightly different. Now, look what happens if we just perform a linear interpolation with the factor 0.5 between these two matrices. We end up in zero matrix, so which is surely not a rotational matrix. So this shows us that we have to be careful where we want to interpolate the rotations. One way how to deal with this is to store the rotations explicitly in a form of a rotation and then perform the rotation process so the angle will be then parameterized. Let's say if we have along just in one-dimensional case, or I mean two-dimensional case, if we want to perform rotation, if our object is rotated first 30 degrees and we want to rotate it into 90 degrees, then we will perform 60 degrees rotation between from one position to another. So we can always, based on the rotational component, create a rotational matrix. So not interpolating the rotational matrix, but interpolate the angles and then create the corresponding rotational matrix which will rotate our object into the corresponding angle which we interpolated. This is one way how to do it. And in 3D, we have the possibility to have three axes of rotation. So that would be the x-axis, the y-axis, and the z-axis to rotate around. And by this, we can express any orientation in the 3D space, any spatial orientation of our object as we want to have it rotated. There is an important aspect, and that is that our rotations are applied after each other, and we know that this will be these operations will be associative but they will not be commutative. So exchanging the axis will change the way how the rotation is done. What we can do here is that we have a certain order, and for each axis we have a starting orientation, and then we have a destinational orientation, and we have the angles between these around which we rotate our object around these three axes. And we are then interpolating along all of these axes, and for between states, we are sort of interpolating so that we create always a partial rotation around each of these axes until we reach the desired position. So this will in general work, and it will create in many cases a reasonable transformation of an object. However, it will not always work. And the problem here is that we might end up in something what is called a gimbal lock. I don't want to go into very details what the gimbal lock is, but in principle, you can imagine that if you have a gimbal, which is an object shown here, you can rotate object around three axes. But once you would, for example, rotate an axis and into another axis so that they are aligned, then you create the gimbal lock. Once again, this is the gimbal lock is an object which, or the gimbal is an object, a physical object, which has a hierarchical ordering of rotations. The most outer rotation will be around the y-axis. So if we rotate around y-axis, the entire system rotates around the y-axis. However, if we rotate around the z-axis, then we are not rotating around the y-axis, and we are rotating around z, and we are rotating around x. And when we are rotating only around x, then we will not be rotating around any other axis. So we have to be aware that if we are rotating in this setting of so-called Euler angles, so these are the type of Euler angle representation of angle rotations for animation, then we need to understand that one axis is hierarchically above another axis and another axis. So we have three axes of rotation, while there are not they are hierarchically organized with respect to each other, as shown in this gimbal lock. That means that what can happen, for example, if we rotate around the second axis, which would be the z-axis, we can rotate the rotation axis of x into the y-axis. And that would mean that we achieve this lock. This is shown here in this case, where we will have the gimbal lock configuration, and we are then not able to we sort of lose one axis of rotation because one axis is aligned with another one. What does this make as a problem for computer animation? The problem which causes a gimbal lock is that it creates an animation of object from one orientation to another orientation. However, the path how this object reaches the one orientation from another orientation might be highly unintuitive. So in summary, if we have a good ordering of axes for a particular setting, then there will be a good orientation change through computer animation using Euler axis. And if we have an unlucky situation that we are causing gimbal lock, then we will have a highly unintuitive orientational change between the original orientation and the target one. So the Euler angles are not very suggested for performing the the interpolation of rotation in computer animation. And this holds for Euler angles, which are so-called bound to the object, or the fixed angles, which are the coordinate axis. So I so far was telling you about the axes which are in the local coordinate system of our object, and that's called the Euler angles. And then we have the fixed angles, which will be the world coordinate axis. The same thing, just that we are performing the rotation in a different space, not in the local coordinate space, but in the world coordinate space. So fixed axis rotations or the Euler angles can be an approach how we can animate rotations. However, we have to be aware of the pitfalls associated with the pinball walk and have to be ready to accept that our transition of rotations might look unnatural. Optimally, we would like to have some rotational approaches which would have a very simple way of animating it as a component-wise multiplication with a certain factor, which will be performing the interpolation between two rotational states. And this can be actually achieved by the concept of an axis angle rotation. So axis angle is a concept where you define one axis in space. So you will have your coordinate frame and in the world coordinates, and you define an arbitrary axis, and around this axis you rotate. This representation of rotations can guarantee you orientations in all orientations in space of a particular object, and also it allows for a easy animation. So how can this be achieved? If you will have an axis angle rotation representation of the rotations, so not three orthogonal axes in either object space coordinate or in the world space coordinate, but just one, and one angle around which we should rotate, then two such representation of orientations can be animated in a way that first the axis of rotations will be interpolated and the angles around such axis will be also interpolated. And if you just interpolate these two, then you should end up in a natural interpolation of rotation. And this can be achieved either by explicitly having this angle axis representation or having it implicitly present in a manipulation with so-called quaternions. Quaternions is a mathematical structure or mathematical object which is a distant relative of complex numbers. It also has a real part and imaginary component, only that there are three imaginary components and not only one. In our case, we can use the quaternion and the arithmetics associated with quaternions for representing the axis and angle. So this S would be standing somehow for angle, and this V would be somehow the axis vector. Not completely as in the axis angle representation, because you can see that it is a little bit intermixed. In the quaternion representation, in the first scalar value, we will have the cosine of the angle under which we want to rotate around a particular axis. And in the second part, we do have a normal of our axis around which we want to rotate. However, scaled by the factor of the sine of this angle. So, and this representation will allow us to perform a component-wise interpolation of these values as x, y, z, and will result in a smooth interpolation of rotation without any gimbal lock, without any artifacts associated with it. Here you can see how basic arithmetic operations on quaternions look like. So as you would expect, the addition is pretty simple: scalar addition and scalar and vector addition. The multiplication of a quaternion with a scalar is the multiplication of all components with this scalar. The representation of multiplication, however, is a little bit more involved. It includes the information about of a dot product between the two vectors and somehow subtracting from the scalar multiplication. And here we can even see that there is, in the vector part, there is even a cross product. So the multiplication of the quaternions is a little bit more complicated, but it will be a crucial tool for us for representing rotations. And how this can be achieved. One more thing to know: an inverse to a quaternion we can have simply as a reciprocal of its magnitude and the inverse of the vector. So other orientation than the original orientation of the quaternion's vector. How can we use this for calculating rotations? Well, if you have a rotation of which you would like to rotate a point around, you can simply calculate the rotation using this formula. So you first need to have a representation of your point as in quaternions, and it will look like this. You have simple coordinate of the point, and for the scalar part there will be 0. And then you will have the quaternions, a quaternion of your rotation, and you need to perform multiplication with that quaternion, and then this whole is multiplied with the inverse of that quaternion, which we have been discussing before. With this, you will obtain another point in space, so the Q prime P will also look like, will have a structure where there will be a 0 in the first part, the scalar part, and in the vector part, let's call it a P prime, will be the new position of your point, rotated. And we can compute this Q if we have two rotations and we want to perform an interpolation between those. We can perform a component-wise multiplication of this component-wise multiplication of these quaternions with a scalar value as a weight between 0 and 1 in order to perform a linear interpolation between those. Note, however, that if we create such a quaternion, what we will end up with will be something where we have, imagine these are two quaternions shown on this image, and if we will be component-wise interpolating between those, what we will achieve is these intermediate quaternion values, which will be not of a unit length. And this will be a problem because it will be, while your rotation will be still possible, the rotation will be not equally having the equal speed. The speed will be varying, and you might need to change that. And this change, in order to make it that the rotation is constantly moving, you simply have to renormalize the quaternions so that they will be of a unit length again. Once the quaternions, the interpolated quaternion, will be of unit length, meaning that you simply divide it by its magnitude, then we can use this quaternion for interpolating rotations and even with a constant speed. So the quaternions are really the solution for performing rotations in computer animation because it avoids all these necessary circumstances which are associated with gimbal lock and Euler angles or fixed angles representations. Deformations are often associated with 3D modeling of geometry. However, these deformations, if they are parameterized over time, they are also relevant for computer animation. And indeed, deformation is often used in computer animation to simulate certain effects of soft bodies. Should it be perhaps some object like a muscle which is deformed upon changing the position of the limbs, or other objects which are typical for organic representations. Some deformations can be represented by procedural functions, where we have a particular function that takes in some input points of our object and generates some output points based on some deformation parameters. For example, we could have a procedural deformation which will realize bending. We see this original shape of the object and how the resulting deformation will look like. And if we are increasingly changing the parameter of the level of bending, we can create an interesting animation relevant for some applications. Another way how we can represent an animation through such a procedural deformation could be taper. Taper is also very easy to explain. We can see that its formula will be here. So we have an XYZ coordinate, but this is the Z coordinate, and with an increasing Z, we will be dividing our X and Y coordinates with the Z value, so that the higher it is, the smaller the X and Y coordinates will be, because they will be scaled by 1 divided by the Z coordinates, plus 1, just as a detail. So such a procedural animation can be also represented over time, where such a vector is also weighted by, let's say, the T value, and with the increasing T, this level of tapering will be also increasing. And there are other possibilities what can be set as a procedural animation along one axis, like for example the twisting, where we will be performing a rotation, which will be the magnitude of the rotation will be guided by, again, the magnitude of the Z component. This would be somehow the global deformations which we could use upon objects, and we could perhaps animate them. There are other deformations which could be relevant, and first, the one relevant deformation is the deformation by pulling. Imagine that you have an object, and then this object is being then dragged by sort of grabbing on some of its geometry and moved further. If this object is rigid, the entire object will be moving from one place to another. If this object is very fragile and fixed to one position, if you are dragging a vertex, maybe only that vertex will move and the rest will stay in its position. But for more softer objects, you can imagine that there will be certain deformation going on. Like, for example, here, when we have been moving this one vertex from the position, its original position, depicted here, into the target position. And not only its position has been changed, and the triangle's faces associated with this one vertex, but also there has been some scaling or changing of positions of the other vertices which are somehow adjacent to it. And we can have a certain function which will be defining how the change of other positions of vertices propagates based on the change of one of such a vertex. And this distance function can be scaled by, for example, a Euclidean distance. So the more far away these points are from the original position of our vertex which is being tracked, then the more far away they are, the less there will be an impact on the movement of this vertex to these vertices. Or the closer they are, the more they will be moving along, so to say. There could be another distance function, not only Euclidean one, like, for example, shortest path along edges. Remember that we are dealing with geometries, and each position of two vertices can be expressed by the relation between two vertices can be expressed by a path along this mesh. So the shorter the path is, the more this point will be also moving along. And last but not least, we can talk about the geodesic distance on the surface, which could be the distance function. Geodesic distance means that we measure the distance directly on the surface. What is the closest distance of a path which is on the surface, does not go necessarily through the edges, but also through the faces, which connects the two faces. It's not the Euclidean distance necessarily, because the Euclidean distance can go not only along the surface, but can go sort of in the air as well, while the geodesic distance is really on the surface of our object. So, in case some objects will be, or vertices will be not affected, they will stay as they are, and the other vertices will be also displaced, but the weight of how much they will be displaced will be attenuated by a certain factor based on the distance metric which has been chosen. So this is a deformation by pulling, which can be nicely integrated in some computer animation scenarios. Very popular for modeling and for animation as well is the so-called freeform deformation. We have been already talking about a Bezier representation or other curve representation in the previous lecture on curves, where the Bezier sort of control points will be representing a rough sketch of the curve, while the curve will be smooth within the convex half of this control points. And similarly, we can think of a so-called freeform deformation, where we will have a rough representation of our geometry, somehow depicted by these few cells of this object, which are acting upon another object and creating a deformation. And this deformation can be created by a displacement. So there is a vector field encoded in this freeform deformation, which will tell how much the particular vertices should deform when they are within our freeform deformation object. And this freeform deformation can be changed either with the various forms of interpolation. It could be a linear interpolation, or we can also imagine that we are using such a freeform deformation representation with using a more advanced scheme, more smooth scheme, such as, for example, the Bezier representation. Bezier concept can be also used not only for curves but also for surfaces and also for volumes. So it just depends how many dimensional this Bezier construct will be. Keep in mind that this freeform deformation object can itself be animated. Either its position is animated or the strength of this displacement is animated, or the size of the object of freeform deformation grid or cell set can be animated. We can see here one example where we have a freeform deformation associated with a certain set of vertices on this schematic example, and by changing our freeform deformation, we will be changing the positions of these individual points. So you can see that these points are keeping, so if the point is sort of in the middle, between one axis and another axis of this cell, such a point will remain in the same position, likely with a linear or bilinear interpolation scheme. With a higher order interpolation scheme, there will be rather some smooth change in the position. So we can see that it is visible on this second example here, where you can see its position and the displacement of our object will still keep our point within the center of the cell, while the cell has been deformed. And by that, we are implicitly defining the position of our more detailed mesh object. So the freeform deformation is the basic principle that the mesh which we are deforming is a coarse representation with a very few geometric elements, vertices, and it is deforming a much more finer tessellated mesh, and which is much easier to deform this way than to move the individual vertices of such a mesh. So the freeform deformation can be used for 3D modeling, but also can be animated and then becoming a useful tool for computer animation. We can see here the representation how a Bezier approximation would look like for a given three-dimensional object. So until now, we are somehow familiar with such a representation of the Bezier, where here we have our control points positions described, and here we have our Bernstein polynomials, which are consisting of some polynomials of the degree k and n minus k, and then the binomial coefficient n over k is the multiplier of such a term. And this is all summed together forming the blending. Now this is for one dimension. You can also imagine that making a two-dimensional Bezier could result in a sort of a surface, and making a three-dimensional Bezier representation will actually create a smooth volume. And such a volume can be therefore used for a smooth representation of the deformation using the FFD, which stands for the freeform deformation approach. A very special category of animation in computer animation, but also in a traditional animation, is the character animation. There are several aspects to it and several ways how we can animate characters. Typically, we would be defining a character, and this could be a human character, but also an other biped or quadruped animal. We would typically define a certain skeleton to it, which will be, if you like, a stick figure, which consists of bones and joints. So we see several bones and joints, and these form a so-called kinematic linkage, which is a hierarchical organization of these bones and joints. Meaning that if I would act and perform a rotation of an shoulder joint, for example, of this character, the entire hand will be rotated. You might remember this from the scene graph description, where we also had this hierarchical organization. And a similar, if not the same, hierarchical organization, we will be dealing with the character animation. There is a special term for setting up an animation of the bones, which is called the rigging. So if you see in computer animation the term rigging, you know that this is basically setting up the skeleton. Usually, it is not the skeleton which we would see on in the character animation, but it is the complete body, including a skin. This, therefore, we need to establish some relationship between the bones and the skin. And this relationship is partially inspired by the human nature. So, for example, we can have various ways how we associate the skin to a particular bone. We can either do a so-called rigid skinning, where vertices on the skin are directly attached to a particular bone, and if the bone has been displaced, then these vertices will be displaced with it. So they are in a fixed relationship with each other, and so that the bone is sort of hierarchical parent to all these skin vertices. This can be defined either through rigid skinning, or another approach is a soft skinning, where there is no one bone which is acting upon a part of a skin, but there is also a transition between the two bones. For example, at the joint area, we will have a transition which bone is sort of responsible for which part of the skin. And this the motion of the skin will be then a linear interpolation between these two bones. We can see this transition here, where there is a smooth transition between one bone to another one. And in this intermediate stage, there will be an influence of both bones on the skin. Sometimes we are even defining an intermediate level between the bones and the skin, namely the muscles. If we want to go even further in a correct anatomical animation, then the bones will be attached to muscles, and these muscles will be acting and contracting, which will create deformations on the surface, which will then be deformed accordingly. This will result into even more realistic deformation of the soft anatomical tissue. How do we animate this structure, this rigged structure? Well, let's focus on the bones now. We know already what the skin will do, given that we animate the bones. And there are several methods to animate the characters. We will be talking about two methods predominantly, and they both are in the category of kinematics. Kinematics is similar to is a type of animation which is not based on forces. So we do not have a description of forces which will then create accelerations, velocities, and then change of position, but we are dealing with a certain description of a motion. And the forward kinematic is an explicit definition of the motion, where we are defining how a particular joint is moving. And with this, we can reasonably effectively model typical motions of which are of cyclic pattern, which we then can use on in the case of character animation. Like, for example, we can define the stride of a foot and leg. How does the different joints change their position in one cycle of a walking or running? So with this, we could explicitly define that there is a certain angle animated uh, of the hip joint, and consecutively with that, there is an ankle and the knee joints are also performing certain rotations in various parts of this stride. This can be either directly authored by making these changes of the angles explicitly in somehow an angle versus time graph, or this can be also taken from real observations. What do we mean by that? This could be recorded from a sequence of a walking or of a running of a real person. We will talk about that just in a second. One more thing which is important to mention, that forward kinematics is working with this kinematic linkage. So there is a hierarchical relationship between the joints, and that these joints have a so-called degree of freedom and constraints. That's how they are characterized. Degree of freedom for a joint means if a joint would have just 1 degree of freedom, it would be a rotational joint which could rotate just by one angle. Think of your own joints which you have in the body. Like, for example, the joint which is attaching the femoral bone to the pelvis is a ball joint which has actually 2 degrees of freedom. It can rotate in two different directions. You can imagine two rotations as you are performing the movement with your lower limb. However, some people would say that a hip joint would have even 3 degrees of freedom, because even within the socket where the ball joint is located, the ball can rotate around the axis, which is defined by the actual bone, and can rotate within that socket. So that would be the 3rd degree of freedom. So this concept of degrees of freedom characterizes the joints, and the joints can have up to a single joint can have up to 6 degrees of freedom, meaning 3 degrees of freedom which are rotational character and 3 degrees of freedom of a translational character. Our joints rarely have those amounts of degrees of freedom, and in addition, they are constrained. Think of your knee joint, for example. If you see the rotation of the knee joint, you certainly see that if you straighten your leg, your lower part of your leg cannot rotate even more, because once the leg is straight, that's the final position. There is a constraint in the knee joint. So our joints will be defined by the degrees of freedom, defining it, what type of joint it is, and with additional constraints on the range of these degrees of freedom. We can typically create a kinematics by either authoring or by measuring this using various devices. A very popular method, especially in computer animation for film industry, is the motion capture. Practically all the animated characters in movies, which are in some degree computer generated, are based on motion capture data. These are taken from various measuring devices which have been developed over the last decades. There is, for example, a magnetic type of device which is measuring very precisely how are the different parts of the animated character moving, rotating, positioning themselves. However, such a magnetic tracking, as it is called, sometimes has a trouble to be when it is exposed to some other magnetic field, like for example, in a building, if there is an elevator, that might cause problems and errors of this motion capture based on magnetic tracking. And also, it requires a lot of cables to carry with in order to realize such a magnetic tracking setup. However, the advantage is that it doesn't require so-called line of sight. The line of sight is a crucial aspect in so-called optical tracking, which is, by the way, probably the most popular one these days for motion capture. A character, as we can see here, is performing some animation sequence of playing golf and hitting the ball with a club. And there is a lot of small dots which are characterizing the positions of his anatomy during this process of the capturing this particular action. And all these balls are recorded, their position is recorded from several cameras, infrared cameras typically, which would then record the motion of these balls, and this motion will be translated to the motion of the limbs and to the orientations of the joints. So it will be remapped from the actual positions on the skin or cloth of the character onto the bones and the joints. And therefore, these locations are often located somewhere near to the joints. And once this is done, then we will get a synchronized animation or positioning recording over time. How do these joints change over time when performing a certain action? And this information can be through forward kinematics directly mapped to our bones, which will then animate our characters. While this technique works and is reasonably popular, it has certain problems. For example, if you will be animating a character and this character is moving along a certain surface and you have pre-recorded data of the movement, you will often realize that this motion capturing results into somehow sliding motion on the surface of on which this character is supposed to walk. So the sliding motion is a certain decoupling between the displacement on this surface and the speed at which this character is being moved. Therefore, there is another approach which can be combined also with the forward kinematics approach, which is called the inverse kinematics. Inverse kinematics, I am sure you have heard about it, and in the computer animation literature and language or slang, the IK is typically used for a declarative approach to define joint rotations. By declarative approach means that we are defining a goal. We define where we want our our hand to be located at a particular time, and the animation of the joints will be then performed uh, will be calculated based on this end position. So it's a sort of an inverse problem, and the inverse kinematics has a very good approach to calculate this information from the end effector position to the rotations or repositionings of the individual joints. The end effector, as we call it, is if we have, for example, the hand, and we have this character here, then the hand will have the palm or the hand as the end effector. And maybe there is a mug on the table, and we want that this end effector is getting and holding the mug. So we want to change the position of our end effector from this position to another position. And in order to achieve that, we need to calculate what is the angle at our elbow joint and what is the angle at our shoulder joint, which realizes this motion. And perhaps even if we have certain angles here so that we can hold the cup and not only come near to it, we will probably need some angles associated with the wrist joint. So the animator specifies the end effector's target position, and the calculation of the joints is realized by the system. We can analytically calculate the positions or the vector of joint angles in order to reach the desired position, sometimes on simple systems, but in general this is not utilized, and often iterative approximative methods are used which calculate us the inverse kinematics. Let's discuss it, how this can be done. Well, if you are thinking of the positioning of an end effector from, let's have here certain angles. This is our end effector, and we want to position it somewhere, let's say here. We will need to understand what should be the constellations. We understand its original position, let's say x0, and we understand the x0, and the x1 will be the target position where we want to end up, or maybe not x1, but xe as end, so that it doesn't confuses us with this x1 here as a component of this vector of the positions. So we know the positions, and we know a vector alpha, so this is alpha 1, this is alpha 2, this would be alpha 3, and we know that the positioning into the desired position, the xe, is a certain function of alphas. So we change the positioning into the new position, provided that there is a solution from the original position to the end position. And this function alpha can be defined as, let's say, the difference between xe minus xo is equal to the delta x, which we have described here. This delta x can be described as derivatives of this unknown function with respect to the different angles. And by applying a certain delta of these angles, which we also do not know, we can reach the desired position. So while we do not know these partial derivatives at the beginning, we can actually calculate them and store them in the so-called Jacobian matrix. And what does this Jacobian matrix capture? In the row, we have various elements of our angles. So here we have angle 1, angle 2, angle 3, angle n. So we have as many columns as we have angles. And then we have, for three-dimensional space, we have three dimensions, x1, or 1, 2, and 3, and these we are evaluating. How does each small change of my rotation around the joint A1, how does it change for the position in the X coordinate? How does it change in position with the Y coordinate? And how does it change my end effector's position for the Z coordinate? We can see it very clearly here on this drawing. So we have our alpha for the knee joint, and we are having a very small delta change of the alpha, and we measure, so this change is, let's say, I don't know, 5 degrees, and the delta x is some measurable distance. And this amount, by this very small difference of angle, how much does this x-coordinate change, will be stored in our Jacobian matrix as one of these elements. For example, here, if this would be the alpha 1. And then we have, by evaluating the small changes of angles with respect to all the coordinates, we will end up by filling out this entire matrix. And once we have the Jacobian matrix, then we sort of have only one unknown in this equation. We know what is the change of x because we know what we declared. We want to change the position x into the end effector's position. So we know the delta x. We also now know this Jacobian. The only thing what we don't know is how much the actual change of these angles should be so that we can get to the position of the end effector. And in order to find out, what can we do? Here is a vector, here is a vector which we don't know, and here is a matrix. How can we calculate this unknown vector? Well, we can bring the matrix to the other side and by inverting it. So here we have our Jacobian matrix, and we need to invert it. Well, that might be a problem because sometimes if we have, for example, a matrix which is not a square matrix, we will have a problem with inverting it because we will have more columns than rows, and such matrix is not really invertible. So it is an over-constrained system or has too many degrees of freedom, and because there are several solutions, there is often not just one solution of the constellation of the angles. But normally, we would need to simply calculate the delta alpha, the changes of the vector of angles would be equal to delta f delta alpha inverse times delta x. And once we will have this inverse, then we can compute it. As I said, the inverse is problematic because in cases where we have more of joints than spatial axes, then we will have a non-invertible matrix. Therefore, it is often, instead of the inverse, we compute the transpose. So this matrix will then not be inverted, but it will be transposed. And we will then calculate this solution with the transpose. However, we will calculate only one iteration of this entire process because, as you can understand, these partial derivatives of the change of the function with respect to the change of the angles is only giving us somehow a small validity of this change. Therefore, if we will have two big changes of angles of the spatial positions, then we will actually not reach the final position. We will approximately go in the right direction. But for getting to the perfect position where we want to be, we will need to calculate several iterations of these inverse kinematics. So we see here that at each step of the inverse kinematics, we end up in a new position. And this new position requires us to compute the new Jacobian matrix, because the change of angles with respect to the x, y, and z coordinate will be different at each spatial position. Once we calculate it, then we can apply the equation which we had before, where we are having the inverted Jacobian matrix or transposed, and then we can calculate the new values for the internal joint parameters. Afterwards, we already know what should be the rotation, and then we apply the forward kinematics so that we reposition these joints to the new locations. And if we are satisfied with the location, then we stop, because we say we have reached the position. And if we are not satisfied, then we perform one more iteration and try to get closer to our desired end effector position. You can see that the end effector can be reached in various ways. You see here two examples of the different constellations and rotations of our joints, where the end effector can be reached by both of them. If we have a more complex system, we can even see that there are different angles which we can calculate and we have several degrees of freedom in order to achieve a certain position. And of course, even imagine a situation where you want to reach an object, but your hand is just simply too short in order to reach that point. And there will be zero solutions. So the inverse kinematics also can lead us to a result which will get our end effector position as close to the desired location, but it in fact will never completely reach it. And in such a case, we will be never ending in this loop, and therefore we will have to have additional tests whether actually there is a certain convergence to the position or there is actually no solution. Another category of animation which is using forces. So remember I told you at the beginning of the kinematics that the kinematics are not based on forces. It is an animation which uses a description of the change of certain values of joints and positions, but it doesn't work with forces. The physics-based animation, on the other hand, is using forces, and it uses a procedure which is a simulation of some abstraction of the real world into some physics equations. And with that, we can animate a lot of natural phenomena. We can animate cloths, we can animate gravity, we can animate the planet system orbiting around the star. We can animate fluids, soft bodies, cloth, and many other objects. We can include into the physics-based animation things like wind, temperature, and other physical quantities that would then affect the simulation process. It really is the simulation is a solving of differential equations step by step. So it's an iterative process again, and we will be going through the simulation, simulating the real-world phenomenon in an iterative fashion. And this can be done in the loop of defining forces, and these forces are acting upon our objects, are then forming certain accelerations, certain velocities, which will then ultimately lead to change of the positions. And of rigid objects, this change of positions will be without the modification of the geometry of the object itself. But for soft objects, we can also have a change of positions of the vertices on this soft object for each vertex independently. While this would be a separate lecture or even a lecture series on physics-based animation, I just want to give you a flavor that there are several types of forces even. I don't mean only a force like some forces are gravity and some forces are, let's say, forces within the environmental system, but there are positional forces and there are rotational forces. And both of these are necessary to maintain in a system in order to end up in a realistic, physically based animation. When we are discretizing the phenomenon of physics into single steps, we will need to use some integration approach in order to move from one time step to the next time step along the simulation or along the animation. And for this, we can use the finite difference methods, and there are several at hand. The most simple one and the obvious one will be the explicit differencing, where we have a certain function as a set of forces, let's say. We sum up this set of forces upon a particular object, and we are calculating then the one resulting force, let's say, in the simplified case, and we calculate out of that the acceleration and velocity, and then based on the velocity, we are calculating what would be the position at a time step and at the next time step. So, and with this, we can as we are defining an instantaneous quantity, that will mean that our change of position based on a certain velocity vector will be just approximated. And we might end up in a situation when our time step, delta t, will be too large, that we are jumping to a position which will be way far different than the position where we actually should be. Imagine that we are animating a circular position, and with this explicit differencing, we will be then calculating velocity and its tangential vector. And depending on how big this time step will be, we will end up in various positions. And you can see that with increasing time, we will become less and less simulating a rotational effect, but this circular motion will actually end up in a motion of outgoing spiral motion that will then end up in something completely wrong. So explicit differencing is a very simple method how we calculate the new time step. However, it is also very unstable. Therefore, we need generally different integration schemes which will result in a stable solution. The implicit differencing will end up in the stable solution, and while they are more computationally costly. We can see that the first description is defining as the temporal variable. So where are we within the system in the next time step? And but we also can have a spatial variable. So we are not only evaluating the gradient in temporal domain, but also the gradient in the spatial domain. We will often have such a description where both the space and time are the subject of differencing or differentiation. With this implicit differencing, what we can calculate is we can calculate um, the future time step in a stable way, but we will be involving more unknown variables from the future. So just calculating one position will not result in we will not be able to solve this. We will rather need to solve entire system of equations in order to have the solution for the implicit differencing. Let's have a look at how a typical physics-based animation loop looks like. We have a mass of an object, we have its velocity, and then we are acting upon this object with a certain force. Then this force will define as the acceleration, and this acceleration will define as a new velocity, because our current velocity will be then added with the acceleration to form the new velocity v prime. And in order to have an define a velocity at a position which is like a halfway within the iteration step, then we will generate an average velocity and move the object just halfway within the half of the time step. And then we will again have a next iteration and perform the same. This loop can be observed here, where we start with the forces and then we calculate accelerations. From that, we will be calculating the velocities and momenta, and finally we will end up with the positions. This is in general the framework of a physics-based animation. There is always a different equation to solve. So you might want to have some simplification of Navier-Stokes equation for the simulation of fluids. You might want to have some temperature, thermodynamics equations to solve, etc. Depending on the application context, what is actually simulated in this animation. Generally, we are not so much concerned in computer animation with the physical correctness, but rather the visual plausibility of the result. And physics-based animation can be considered as a special case of the so-called procedural methods, where we are performing a certain function, certain set of equations which are governing our motion. And these can be physics-based, and then we are talking about some physics-based animation using forces and having a dynamical system, or it could be kinematic-based, where we are having a certain equation defining our kinematics. Like, for example, here we have a description of a wave. So we will have a wave where we, over time, are changing and oscillating with a certain position. So we have our wave, and we have a certain description of based on the distance from the origin. Let's say we have a certain value of the of our wave, certain value along the y-axis, which is governed by this cosine function, but we have its position as far the further it is along the x-axis, the more different will be the cosine value. This is a classical cosine function. But then we have also, so this is this factor, and then we have also this factor, which is the temporal one. So this temporal variable here will be telling us something about how are we over time changing these points. So while such a point will be initially with the t equals 0 here, then over time it will be oscillating in this position. So this is the description of the wave, a one-dimensional wave. The last term here is defining as certain phase shift. So we might want to start the wave at a certain position, as I here started it not for the cosine equals 0, but for, let's say, cosine equals some value, let's say cosine of 90 degrees, or maybe it is a cosine of 45 degrees if you like. It is also somehow above, which is not modeled here. Here could be some C value, which will, so that we do not have negative values. And then we have some kind of a magnitude of our wave, which will be showing us, defining us what is the height of the wave, so to say. And if we are performing this animation and changing the parameter t from 0 to 1, let's say, we can see, observe how this results in an animation of the wave. There could be many other procedural techniques defined for animating the motion, and they could implement a certain phenomena, such as, for example, a random walk or other characteristics, maybe a motion of a geared system, a set of gears, how they are acting upon each other, and creating motion of a certain vehicle, or, for example, the functionality of a watch. Then we have other types of procedural animations, which are called agent-based systems, where we are having certain elements in the scene which have certain rules, and upon interaction with other agents, these rules will be executed. One simple example of that could be a cellular automaton, which have few rules, which is called, in this case, this is the so-called game of life. The game of life will tell you that if there are 3 living neighbors, so 3 cells which are black in this case, around a certain cell which is dead, make the dead cell alive. So that one cell will suddenly change from dead to alive. And if there are 2 or 3 living neighbors, they will still be alive. Otherwise, the cell will turn dead. And this will create you various patterns of this cellular automaton, which tries to somehow simulate the living potential of some cell cultures. There could be other agent-based system where you simply define what these agents are doing upon coming to a close vicinity. So they might be wandering around, they might be walking, they might simulate a pedestrian walk who are crossing the zebra crossing, and if they are colliding with each other, how they are avoiding. So this could all be defined in an agent-based system. And also, such agent-based system can be the realization of the flocking behavior or other crowding behaviors, as we will discuss them on the next slides. Before that, however, we will look at the very famous approach of L systems, which are used in simulating the plant structure. And also, if applied carefully, it could also simulate as the plant animation. the emergence of a certain shape. We will have here one example of such an L system. There is a certain grammar in the L system which is defining some spatial characteristics, and then there are symbols which are either terminal, which are not replaceable by other symbols, or there are non-terminal symbols which are defining rules how these non-terminal symbols can be replaced into other non-terminal or terminal symbols. So we typically start with the symbol S as a start, and this S is then transferred into just one non-terminal symbol A. And we can see two so-called production rules here, where the A can be either changed into another non-terminal symbol B, or a more complex set of non-terminal and terminal symbols as described here. The terminal symbols here are the following. The at will be the draw a circle command. F will mean move forward, so it's a translation. Plus will mean turn by 60 degrees. And the brackets means that you are popping and pushing certain transformations. So once you get out of the bracket, you are forgetting the transformations which were applied for the objects within the bracket. And then you can apply these rules until you end up in a sequence of symbols which only are the terminal symbols. And this sequence then defines you a certain shape. Let's have a look at an example of such an Lindenmayer system. So here we have an development of the production of these rules. You can see that in the first case, we have the S to A. So we are having this first step here. In the next step, our A goes to the more complex definition of A into the push and pop of a certain transformation for B, and then forward move to A. So this B is rotated, however, the point B is then just drawn at that location. So we rotate the B, but it doesn't really change much. And then we forget the rotation, and then we moved forward and have an A position. And this production, the B, we will be changing for FB in our bracket, and the FA, we will be changing for F, that stays, and then A will be changed for this production rule. So what will that mean? That will mean that we are first somehow going from this position to rotation and then forward to, so rotation 60 degrees and then to forward to B. So this is this part, this is this part. And then we forget the transformation, and then we move forward with this F here and have another B and rotation of that B here with this plus. However, we forgot this rotation, and then we have one more translation of the F and A. So we have the third iteration of applying this rule. The fourth level is drawn here. In this case, we are performing the rotation and twice F, 1, 2, and then we draw the circle with the at symbol, which are all the terminal symbols. Then we again pop all the transformations, and we have a new transformation, which is just F, move, and then we rotate at this position, and we move and place the B here. And the final step of this iteration step is to just go forward and have a B. And the very final iteration, where we just end up in the terminal symbols, will be the following one, where we have the F after the rotation, and then we have the draw circle, then we have one F up, and then again 60 degrees rotation and F circle, and then the last part is F, F, and circle. So this system has sort of been, through this iteration, represented the final drawing of something which remotely resembles a similarity to a plant. Well, it could, if you think of good rules, and if the author sort of takes time to define good production rules, you can actually end up in very expressive patterns describing the structures. And if you think about that, as it is shown here in this example, that the individual steps can be also animated. So you have seen that our production rule first had just one line, then it had like two lines, and then it had a more complex two lines. And you can see that in each iteration, there was some kind of an emergence of the structure. So if we carefully define these rules, we can also, for the L systems, use them not only for depicting the final structure, but actually for the animation of the growth. So the next and final discussion will be about group of objects. So we do not have just one object, but we have a compound objects, and they are somehow performing a certain animation. A very famous group of objects, which is often used in computer animation, are particle systems. And those are small particles which are driven by the rules of physics. So they are they are emitted somewhere in the scene, and then they are subject of some physics simulation, which makes their motion, which changes their color and animates various properties until this particle sort of enjoys the duration of its life and it terminates. And these particles often have no intelligence, so they do not think of their environment. They often are implemented in such a way that they are only colliding with the environment, but the particles themselves are actually do not performing any collision handling between each other. With this, you can generate firework simulation, spray, explosion, fire, and smoke. And in the movies on computer animation, you can often see that the particle systems are realized for exactly this type of phenomena. So the difference to other groups of objects is that typically the particle systems are having many particles, thousands, hundreds of thousands particles sometimes, and they do not have any intelligence. They are not analyzing their environment in order to know how to act in the next iteration, so to say. The next group of objects are the flocks, where we can talk about a certain level of intelligence. And this flock is an emergent behavior resulting based on, again, physics animation. Like, for example, here we can see that there is some gravity force and an interaction between few members of the flock. So imagine that you are observing a swirling school of fish, or an orchestrated movement of birds, of a big crowd of birds, how they are moving in the air. So this is the simulation scenario which we want to achieve with a computer animation of flocks. We typically would have several aspects of which are influencing the motion. As I said, there are some physical forces which are affecting the motion of a certain object. Then within a flock, the objects do not want to hit into each other, so there is some collision avoidance in the movement. There is a certain goal which this elements of the crowd or flock want to achieve, and there is a certain steering which we can imply to define where we want the objects to go. So this all can be sort of feeded into a navigational module, which will then give us a certain desired velocity, which will then be matched with certain capabilities of our uh, object, a bird, into a certain feasible velocity which this bird can actually achieve, and finally the flight module will then output the adjustments of the positioning of the flight process. So here there are several and often contradictory forces which act upon each other, and then they finally end up in some consensual motion of this member of the flock. Let's have a look at an example where we can see what all forces can be in place. So often this flocking has several forces. First of all, the member of a certain group wants to somehow match the velocities with its peers. So it considers the motion and behavior of other members of the flock. And perhaps this element wants to achieve a average velocity of this of the other members. If a member will be far away from the rest of the flock, there is a very strong force and desire to sort of catch up with the rest of the flock and join them. Then there are certain obstacles in the environment, so that while the flock wants to sort of be compact and close to each other, the members do not want to be too far from each other based on this local flock centering force. The environment might force them to split and then again to join together after this object collider will be passed during their aggregate behavior. So there are several forces and interaction with the members, for example, which can be modeled by rendering the viewing direction of each of these members, defining what is the depth of the depth buffer on this for these members, and if the depth buffer is showing too large distance to another member, then it will evaluate a force which will try to speed up this element to get closer to the member which is in front of the member of this flock. So in sum, we can have several levels of the flock's behavioral intelligence. First of all, there is some physics behavior which doesn't really define any intelligent behavior. It's just that the laws of physics have to be obeyed in this kind of simulation. Then there are certain perceptual aspects where the environment is defining certain obstacles, distances from other flock members, and so on. And this perception is then governing a reaction so that the optimal state of the flock member is achieved. And then there are some other higher level reasoning which can be even higher level of intelligence, which define a certain behavior of the flock. For example, if there is a certain demand on food, but at the same time there is a high danger of being eaten self by a predator, for example, then there is a reasoning stage which defines which of these urges will get then a higher priority. So this closes the discussion about various aspects of computer animation. We have learned several key points which are important for computer animation, such as the interpolation approaches, the arc length parametrization, how the rotations and interpolation of rotations have to be realized, what are the various procedural methods, what are the character animations, forward and inverse kinematics, how does physically based animation look like, other specialized methods like deformations or L systems, and finally the aggregated behavior of a group of elements in a form of some low intelligence particle systems or higher intelligence flocking and crowding. This will be all for today. Thank you very much for your attention and see you at the next lecture.